Greetings. My name is Matt Roscoe. I'm here at the University of Montana, and this is our first lecture, I guess, in content for our course, Geometry for Teachers this summer. Just to give you a sense of who I am and where I'm at, this is me, and here's my lovely office where I'm recording from at the University of Montana. So just a little facial recognition. Let's go ahead and get started. So the thing I'd like to talk to you today about is the three geometries. We often think of geometry as one subject in K-12 education, but really most scholars agree that there are three different views of geometry that we're teaching students in K-12 education. And these three views are synthetic, analytic, and transformational geometry, so I'd like to just define them. But mostly what I'd like to do is to show you how you can use those different views to study different objects in geometry, and I guess what we'll concentrate on this week and later in the course are quadrilaterals. So I'll introduce quadrilaterals and then give you an example exercise that has to do with rhombuses that shows sort of three different views of rhombus from synthetic, analytic, and transformational perspectives. And then the last thing I want to do is do an introduction to how these three views are sort of rolled into one using technology, and the technology we'll use to explore that is GeoGebra. And I'll give a short introduction there too. So let's talk about the three geometries. So teaching of geometry in K-12 mathematics can be loosely categorized into three different perspectives in which mathematical objects are visualized, and the perspectives are synthetic, analytic, and transformational geometry. So what are these three views? Synthetic geometry is sometimes called axiomatic or pure geometry, and it's the study of shape using an axiomatic method that begins with a set of givens, usually we call these axioms, and then builds results, that is theorems, sometimes corollaries as well, using only the tools of logic and the tools to draw points, lines, and circles. So these are what we call compass and straight edge constructions. So we use logic and we use very primitive drawing tools, point, line, and circle tools. What about analytic geometry? Well, analytic geometry is sometimes called Cartesian geometry or coordinate geometry, and it's the study of shape drawn on a coordinate system. So anytime we put things on the coordinate plane, we're doing analytic geometry if we're studying shape. And when we give a shape a measure or dimension, we imply a coordinate geometry grid. So the study of length, area, and volume, which are really big in K-12 education, are analytic geometry topics as well, even though the Cartesian plane is sort of suppressed when we think about it, but we're gridding it out. So in gridding, it sort of implies that those shapes can be placed on a Cartesian plane too, or a Cartesian three-dimensional space. And then the last one is transformational geometry, and it's the study of shape understood according to the size and shape preserving actions of reflection, rotation, and translation, as well as the shape preserving action of dilation. So this is really this idea of movement geometry, and of course the study of symmetry is really big here, but there are three different, I guess, what we call isometric transformations. These are, reflection, rotation, and translation. And what we say isometric means same measure, so it preserves the shape and the size if it's isometric, because same measure would be same size. But then there is one that often is more challenging than the other three, that only preserves shape but not necessarily size, and that's dilation, where we get things that are similar. So the study of similarity, understood according to this sort of action of dilation, is a transformational topic. Okay, so those are the three geometries. Analytic, synthetic, and transformational geometries, and they'll form sort of the backbone of the content for the course. We'll take a week studying each of the three in more depth and do some sort of a content deepening activity in each of those areas. But for this particular week, we're just going to get started by I guess recognizing these three different perspectives and apply them to a common object. So the objects that I thought would be kind of fun to play with this week would be the quadrilaterals, so square, And these are fairly familiar objects in K-12 mathematics, but perhaps you've not thought of them using this sort of these three different lenses. So that's sort of what we're going to do in the example problem that's going to follow here, and as well in your content exercises this week. So the square is a quadrilateral with four right angles whose sides all have the same length. So four right angles, four congruent sides. A rectangle is defined as just a quadrilateral with four right angles. A rhombus is a quadrilateral whose sides all have the same length, and a parallelogram is a quadrilateral for which opposite sides are parallel. A trapezoid is a quadrilateral for which at least one pair of opposite sides are parallel. And then a kite is a quadrilateral whose four sides can be partitioned into two sets of congruent consecutive sides. It's kind of a tricky definition for a kite, because of course you can't just say two sets of consecutive congruent sides, because then that might imply that there are only, I guess, let's say three congruent sides side by side would be enough for something to be a kite if we didn't partition them into two sets. And then the trapezoid, of course, is probably the most controversial definition in mathematics. It seems like a lot of elementary school textbooks say there are exactly one pair of opposite sides parallel, but mathematicians have agreed, and most upper division textbooks agree, that a trapezoid is a quadrilateral for which at least one pair of opposite sides are parallel. And you'll notice that that means that every parallelogram is by definition a trapezoid. So all the trapezoids, excuse me, all the parallelograms live inside the Venn diagram of the category trapezoid. Anyway, so a couple finer points there, kite, trapezoid. Let's go on and take a look at a few example problems. So the first example problem I'd like to do is to construct a rhombus using only a compass and a straight edge and explain the method. An analytic problem might be something like, here's a quadrilateral A, B, C, D. It has vertices given, -4, 4, -3, 4, 4, 8, and 3, 0. So what type of quadrilateral is A, B, C, D, and explain how you know. And then the last thing would be, well, let's take a look at a rhombus and identify its transformational properties, that is, identify the line and rotational symmetries of a rhombus. So let's go ahead and switch over to my overhead. Okay, so hopefully you can see that. Yep. So the first thing we've been tasked to do is to draw a rhombus using only a compass and a straight edge. So compass, something like this, straight edge, something like this, of course. I'm going to disregard the fact that this straight edge actually has a ruler associated with it. We would assume we can't use the ruler in a compass and straight edge construction. In other words, the only thing we can draw are circles and lines, and those lines are not necessarily measured. We'd have to construct a measure if we wanted to use a measure. Okay, so let's go ahead and talk about how we could do that. So the first thing to note is that, well, we're going to have to start with some vertex. So I'm going to just start with the rhombus's first vertex. Let's just call it, I don't know, A. So there it is. I'll start with a point A. Now a rhombus is, a set of 4 points, each of which is the same distance from A. So it seems like the right place to go then is to construct first a circle. Now you could construct first a side, I suppose, but I'm going to construct an arc, a circular arc, with a vertex at A and a certain radius. Now if we think about what a circle is a collection of points that are equidistant from a given point called the center. So all of these points along this arc are the same distance from A. That means that we can pick any 2 points. Let's call, I don't know, let's say this one, and I don't know, this one. I'll call this one B. The point I'm after out here is C, so I'll call this one D. But I can see that B and D are both equidistant from A. In other words, they're 2 potential sides of a rhombus. So there you go. There's one side, and here's another. And what can we say about those two sides? Well, they're definitely the same length, right? And the big question is, okay, so how do we find this point C out here? Then that will be exactly that distance from B and exactly that distance from D. I mean, I can see it's got to be somewhere in this neck of the woods. But the answer again is to use your circle drawing tool. You know, if I put my point on B and sort of tighten my my compass so that the distance, oh sorry, it should be the distance to A is that, right? So in other words, my compass, I guess you can see that now, is exactly that distance from A. And what I want is I want a point out here that's that distance from B. So those would be a collection of points that are exactly that length from B. If I play the same game with D, and of course I shouldn't have to change my compass. No, I don't, right? The reason I don't have to change my compass is because B to A is the same distance as D to A. But if I put the point at D and do the same game and sort of draw a set of points that are that, let's say, given distance, this distance from D, then I find that the one point that's meets the requirements for being that distance from B, meets the requirement for being that distance from D, and I go ahead and draw that in. And of course that's my point C. And I know then that those two guys are the same length, and I'll draw that little dash in there. So, so what did I do? So my method was, one, choose any point A. Two, I guess I drew an arc. What are we going to call it? Let's call it arc M. Draw arc M centered at A. 3, I chose 2 points on M, so choose B and D on M, I guess such that B is not equal to D. I got to be a little bit careful, right, that I don't choose B on top of D, because then I don't have, you know, unique vertices. Let's see, so then what did I do? So I guess then what I did is I drew an arc. The first one I did was centered at B, so I'll call this one N. Draw arc N centered at B with radius BA, right? It was the same as that. And I repeated that for the other arc, so LMN, let's call it O. Draw arc O centered at D with radius dA. And let's see, 6 would be what, define C to be the intersection of of N and O. And then I guess the last thing, connect quadrilateral ABCD which is by construction a rhombus. Okay, so that's the way we would, I guess, synthetically, using just simple tools like a straight edge and a compass, as well as a drawing tool, I guess, find, I guess, or construct, sorry, a rhombus. back and see what it was that we were asked to do next. We're given a quadrilateral with vertices A, B, C, and D. And the question is, what type of quadrilateral is A, B, C, D, and explain how you know. Okay, so let's go ahead and go back to the overhead so that you don't have to sit and watch me draw and plot points. I went ahead and drew it up and plotted it. But if you want to draw it up and pause right now, certainly go for it. But in the interest, I guess, of time, I have our ABCD drawn up and provided here, and the question is, what type of quadrilateral do we have? And of course, you can see that it appears to be a rhombus. I mean, I could sort of cheat and just check with my compass and straight edge to see if, rely on, well, that seems about that length. That does seem to be about that length. That seems to be, I haven't changed my compass, so it does appear to me like, yeah, it appears to be a rhombus. But the question is how do I know it's a rhombus? And how can I prove this? Let's say analytically. So using, I guess, the fact that we're on a gridded space. You can see that like your tools drastically change here, right? All of a sudden you have, all of this measurement involved, right? I mean, X and Y coordinates, all of which are unitized. So we can start to sort of ask ourselves, well, what is that distance, right? Let's go ahead and see if we can figure it out. One thing I noticed right away, if I want to know a diagonal distance on the coordinate plane, I can always decompose it into horizontal and vertical distances. So for example, if I want to know this diagonal distance, I could decompose this into a horizontal and a vertical distance. And that, of course, is a right triangle. And that particular right triangle has, let's see, a vertical component 1, 2, 3, 4. So it looks like this is 4. And then a horizontal component that's 1, 2, 3, 4, 5, 6, 7. So it looks like this is 7. The question, though, of course, is what is this diagonal distance? And what most people will notice is that, well, that's that's a right triangle. We have this thing called Pythagoras, the Pythagorean theorem, that could help us find that diagonal distance. So a big staple in 8th grade, this idea that that any right triangle, we have a squared plus b squared equals c squared. So so let's see. Let's go ahead and find out. Let's do that up here for step 1, I guess. To find, I guess, BC, we use Pythagoras, which says that what BC squared is going to be equal to 4 squared plus 7 squared, so 16 plus 49. So BC squared is 16 plus 49. So BC is going to be the square root of 59, 65. And let's see, so, and 65 is 5 times 13, so it doesn't appear like there's any simplification of the radical, and I'll just leave it at that. But of course, it's kind of always interesting to think about this from a, well, does this really give us any sense of, I guess, this number square root of 65 could be perhaps better understood if we took a look at what its decimal approximation is. So I'm going to do that really quick. Just hit 65 square root. So it's about 8.6. 8.06, sorry. And, this is kind of fun to think about. I don't know if you've ever done this, but, if I put my length there, it should be about 8 units on the coordinate plane. And sure enough, there's 5, 6, 7. Here's 8 right there. So 8.06 does seem to make sense for length. So in other words, whatever you get here, of course, can be checked against the scale that's provided in the x and the y axis. So we can see that BC is certainly 8.06. Now the big question is are the rest of them 8.06 or square root of 65? And you know, one thing that I can see is that certainly this is going to be true for AD, because for AD, if I come down here and drew in my little square, excuse me, triangle, I can see that it again would be 7 wide, and it would be again 1, 2, 3, 4 tall. So I guess for number 2, I would say that AD is the same length as BC, since I guess AD squared is going to be equal to 4 squared plus 7 squared, or AD is the square root of 65. So that's pretty easy to see that these two guys have exactly, I guess, the same little triangle. I'll draw it in associated with them. But of course on the side here it's a little bit different, right? On the side, if I was going to do, let's do this one for C to D, then I get this really long skinny triangle. It looks sort of like this, and it does have a right angle right there. Not very well drawn, but let's go ahead and think about what this length is. So this length is 1, 2, 3, 4, 5, 6, 7, 8 tall. So it's 8 tall and it's 1 wide, right? So I'll come down here and for number 3, I'll say that, well, CD is going to be CD squared is going to be 8 squared plus 1 squared, and what's kind of neat here is that that's 65, right? So we can see that CD will have to be the square root of 65. So indeed, that one works out to be just like it should. Another length that we'll draw that guy in a little bit. And we can see that that's going to repeat itself over here on this side, or at least it appears to. This real long, kind of like an ice pick type of a triangle on the other side, where we calculate BA the same. So number 4, BA squared is going to have to be 1 squared plus 8 squared, and that makes BA equal to the square root of 65 as well. So conclusion, since all lengths of sides are equal, the quadrilateral ABCD is a rhombus. So kind of quite a different, I guess, flavor of analysis for sure, but you know, same object, right? Here we have no sense of measure, and we're just using circles and the definition of a circle and line and the definition of line to construct, I guess, a quadrilateral out of, a rhombus out of thin air. Whereas here we're given some points, and we're asked to identify what type of a quadrilateral we have, and through a process that uses the Pythagorean theorem, we're able to see that certainly these two sides are the same length, and these two sides are the same length, and they all 4 sides indeed turn out to be exactly the same length, so this guy has to be a rhombus. Okay, let's go ahead and so let's see, last one is transformational. Identify the line and rotational symmetries of a rhombus. So let's go ahead and do that next. So I have a rhombus drawn. I'm sorry, in my last one I should have shown you this, I guess, instead of the one that I had drawn without any explanation as an example of the first and the second problem that we've done. But off we go. So I went ahead and used my synthetic approach to construct a rhombus, just so that I have a nice, pretty exact one. I'm going to go ahead and erase these lines, and it'll become apparent here in a minute why I wanted something that was fairly exact. So let's talk about the line symmetries first. So line symmetry means that, well, I should be able to hold, a mirror up to this and see that it's a reflection in the mirror of itself. So a line of symmetry is simply a line that we can put over the figure such that the figure reflects onto itself. And of course, one line of symmetry seems to be this one. If I place this here and put it sort of, well, that worked out pretty good from the way the view, you sort of peek over the other side and you can see that indeed this guy is reflecting onto itself. What's really neat is I can see the D that's reflected in the mirror there, and of course that's reflecting onto B, which is, I guess, a little bit off there. There we go. So certainly that's a line of symmetry. You can use a mirror. It's really nice to have these in class if you're teaching symmetry. Another really nice tool, if you're not familiar with it already, is the mirror. Unfortunately, this just doesn't work very well in recorded spaces. When I look at it here, you can kind of see it actually there. Some days it seems to work and some doesn't. So what you get is you get a reflection in the face of the mirror on this side that the observer can see, but then you can also see through it, or at least I can, to the other side, so you can really see how one piece is being matched on top of the other. Perhaps if I'll try to do this with the move my, let's see if you can see that very well or not. You can just barely see the D reflecting in the mirror, but trust me that in natural lighting and without digital filter between you and me, that these are just astounding tools because they allow you to sort of see all kinds of really interesting reflections. I don't know if you can see that at all. You can kind of see it, yeah. You can see how this piece and this piece is being reflected and making sort of like a dart-shaped figure that obviously isn't overlaying, but that dart-shaped figure, if I sort of move this slowly, starts to line up when I get to about right there. Anyway, a mirror, really nice tool. These are really cheap. You can get nice classroom sets of them. They're about $3 or $4 a piece. So certainly we have a line of reflection, AC. I'll just draw it in. So number one, I guess, AC is a line of reflection. It makes sense too then that perhaps this BD would also be a line of reflection. And if I pull out my handy dandy mirror, hopefully you can see that that seems to be the case. We get nice reflective overlay. There you can see C upside down on top of A. Kind of hard to see in this view, but through inspection we could say that BD is a line of reflection. So and then the next, I don't think there's any other lines of reflection. I mean, some people might sort of try to think this might be, but you can kind of see that that's not going to work. You can see that those, but by playing around with it, I think that you'll find out that those are the only two lines of reflection. Now the question is, what about rotation? And it seems to make sense that if I call this point A, B, C, D, E, that it becomes sort of an important point on the figure, this spot where the two diagonals intersect, because if I place my, I guess my my pen here, try to do it without getting in the way of the camera. You can see that if I sort of rotate this thing like that, I get it back, right? So rotating it upside down, or I seem to get it back. And the question is, well, what is that rotation that takes C to A and A to C and D to B and B to D? And it seems to make sense that since these all occur along lines, that rotation is 180 degrees. So, and let's see, number 3, A, B, C, D has 180 degree rotational symmetry. So there it is, the 3 transformational, I guess, aspects of the rhombus. So just to recap, synthetic geometry creates figures with very primitive tools like a compass and straight edge, and then advances sort of the givens, things like a circle is a collection of points that are equidistant from a given point, to more complex items like a rhombus. So you advance using logic here. In analytic geometry, we place things on a coordinate plane, and we use tools that are developed there to help us understand figures. If we're given 4 points on a plane and asked what kind of quadrilateral it is, well, it appears to be a rhombus. To check to see if it is a rhombus, what we do is we appeal to the theorem of Pythagoras to try to figure out what the lengths of each of the sides are. And since they all turn out to be the same, this thing's got to be a rhombus. And then in transformational geometry, what we're looking at are these size and shape preserving actions of reflection, rotation, translation, as well as dilation, which of course we didn't look at here, but 2 aspects of the rhombus, I guess 3 aspects of rhombus that are important in transformational geometry is that it has 2 lines of symmetry. These reflection lines happen to be the diagonals, and where those 2 reflection lines intersect, we'll call it E. That point becomes the center of a rotation of 180 degrees that allows the figure to return to itself, so it's got 180 degree rotational symmetry. All right, so 3 different views of the rhombus. Let's go ahead and move forward here. The next thing I want to talk to you about before we end is this idea of using GeoGebra to explore 3 geometries. So what's loosely called dynamic geometry software is this class of software that allows for the integration of synthetic, analytic, and transformational perspectives of shape. And so these things are really important tools for teachers, and I want this course to certainly give you some practice or perhaps some initial instruction in these technologies. So we'll definitely be doing some work in GeoGebra in this course. So we need a problem to explore, and the problem I'd like to explore is a little more in-depth exploration on the properties of the diagonals of a rhombus. So let's take a look and see how dynamic geometry software can help us. And in particular, what we're going to try to do is we're going to try to do this. So let's use technology to create a dynamic quadrilateral that is always a rhombus, and then we'll construct the diagonals, and then we'll create a checkbox that shows and hides the diagonals of a rhombus, and then we'll investigate the properties of a diagonal of rhombus, of a diagonal, and perhaps I should say of the diagonals. And then we'll create checkboxes that show and hide the properties of the diagonals of a rhombus and summarize our findings in a text box. Sounds like a lot, but let's take a look. So the first thing I want you to know is that the technology that we'll use in the course is going to be GeoGebra, and I'll bring a browser down here. So if you just type GeoGebra into a search engine, it'll take you to this one. This is the one I want. So here is the GeoGebra homepage, and you can find all kinds of good stuff here about learning GeoGebra. And the one that might be important to you is learning GeoGebra Classic if you've never used it before. But this is the one that I'll use. So keep in mind that there are some resources here. But what you're probably going to want to do if you don't have it already installed is to get the app downloaded. It's a freeware, so there is no charge for it. And the one that I like is GeoGebra Classic 5. You can use Classic 6 if you want to. It's a cloud-based software, so it is sometimes, I guess, slowed down by slow bandwidth, so that's why I avoid it. I find that schools sometimes don't have the fastest bandwidth, so the Classic 5 runs independently on your desktop. It's a desktop software, so this is the one that you're going to want to download. Once you download, then what happens is you get a piece of software that looks like this. I'll go ahead and fire it up. So here it is. Yours might look a little bit different upon startup, but usually this is the general look of the software. Just to give you a sense of layout, you have an algebra pane and a graphics pane, and the graphics pane, of course, looks like the coordinate plane. Usually it's set up to look like that. If you put a line in the coordinate plane, then right away what you get is you get some things in the algebra pane, which are the way that the line is defined. It tells you what A and B are in terms of its coordinates, and it tells you the equation of the line F. If you right click on it, you'll probably be more used to seeing it as a slope-intercept form. So you can change the format of the line. Of course, this is kind of helpful for learning things like the slope of the equation of a line, or the equation of a line. Here's a line that passes through these 2 points and has this equation, for example. You can control how different things look and act. For example, under options, under labeling, I usually don't automatically label. I don't like labels to always pop up, so I don't label anything. I do no new objects. That way when you do a line, you don't always get the points labeled, but it's up to you however you want to do that. If you right click and I guess scroll, you can select things and delete and get rid of them. File, of course, this is where you do all your file actions. Edit, there isn't a heck of a lot here other than copy and paste, and you can here do a graphics view to clipboard, which this is the way you can make pictures. So copy a picture. Here is the views. You can see that we have algebra and graphics view put up here, but you should be made aware that this also has a spreadsheet view. You can use this like Excel, and that spreadsheet can interact, of course, with, you can plot those points in the graphics view and whatnot. It also has a computer algebra system if you're into that sort of thing. There is an option for a second graphics pane. So some people use this where they want, for example, a unit circle to scroll out the sine wave. So you could have a unit circle in one graphics window, a sine wave in another. There's also a three-dimensional view if you want to play around with 3D graphics. I haven't done much with the rest of these. Options, I guess there's a rounding option. How do you want to round? Labeling options, font size, language options. Tools, you can create custom tools, something we probably won't do in this course, but you should be aware if there's something you do a lot that requires a sequence of constructions, you can create a tool that will do that. You can open new windows here and then help here. But mostly what you need to know about are things like these tools down below, which are all the construction tools. Now they're particular to whichever window. They'll change if you're, for example, if you have the spreadsheet editor up, the tools for the spreadsheet are different than the tools for the graphics and algebra view. But each one of them has nested underneath it a number of tools that are associated with it. So this is sort of the move tool and all of the associated move tool. This is the point tool and all the other different point tools. This is the line tool and the other associated lines, so segment, ray, polyline, vector. Here's a perpendicular tool, but you also see it gives you a parallel and perpendicular bisector, angle bisector, tangents, best fit lines, etc. Here's the polygon tool, but you can also get a regular or rigid polygon or a vector polygon. Here's a circle tool, which you can also do a circle with center and radius, a compass, circle through 3 points, arcs, sectors. Here's the ellipse, hyperbola, and parabola, so your conic sections are all here. This is sort of like the measurement drop down: angle, distance, area, slope. So the measurements. Here are all the transformations: so reflection, rotation, translation, dilation. And then here are kind of the extras, things like sliders, texts, checkbox, we'll do that, a text box, we'll do that here in a minute. You can also import images if you want to analyze geometrically an image. You can put an image on the back behind the coordinate plane and take a look at it. And then this is sort of the move tool, allows you to sort of grab the plane, move it around, and allows you to zoom in and zoom out if you like. Okay, so let's go ahead and start by building a figure that's always a rhombus. So the first thing I notice is that, well, I don't really need to have the grid there. So I'm going to get rid of the grid, and I'm going to get rid of the X and Y axis. Now I know they're back there, right? I can always turn them back on if I want. But for my purposes here, I don't think I need them. So they're just cluttering my display. So I'll start with just a blank piece of paper. Let's think of it that way. And I'll put a point in there. And then what I need to do is I need to build my rhombus. So what I'll do is I'll build my circle like I did, and I'll let the point that defines the circle be one of the points on the rhombus, but I need another point on the rhombus, so I'll put this as another point on the rhombus. And so far, what do I have? I've got two sides of a rhombus. There they are. Oops. Two sides to the rhombus. So now the question is, how do I make, I guess, this last point such that it's always going to maintain the same distance from these 2 points as these 2 points are from the center of the circle. And I think the way we do that is we put the circle here and we draw it such a way that this becomes its radius. That ensures that any point on this circle will have that radius, which is the same as this radius, of course. And I'll do it again from this point. And now I can see that these two circles intersect right here at this point, and that's the point that's equidistant from these two and has the same distance as they are from the center of the circle that was first given. So I'll make that my last point on the rhombus. And so now I could probably get rid of the circles. I've got the 4 points I need. I could probably get rid of the circles. Now, one of the things I like to do in the algebra view is to organize things by object type. When you organize by object type, you can see what are points, what are segments, what are conics, and conics here are circles. So I'm just going to undo those circles, get rid of them, and or hide them, I should say. I didn't get rid of them. They're still there. Does everybody see that? I turn that on and off. But what I have now is I have these 4 segments, which all are exactly the same length. And of course, it's going to survive what we call the drag test, meaning that if I change, that point, if I change this point, that what doesn't change are these segment lengths. In other words, the relationship between these segment lengths. Those segment lengths remain always equal to one another because the construction guarantees that it's always a rhombus. And that's what we call the drag test. If I grab something and drag, do the properties that I want in the drawing remain fixed? So there it is. It's a rhombus. I'll go ahead and label these points. One way that you can group label things is you can click on point, and that highlights them all, and then right click on them and go to object properties. And here I can, let's go ahead and show the label, the name. There we go. So I've got my properties selection just fine. Okay, I'm going to close that window out. So there we go, A, B, C, D. Although I don't like the way it's named, I should probably name this one C. So one way you can do that is just highlight it and then type in a new name, C, and it'll say, do you want to rename that point DC? You hit OK, and it changes it to C, and then the old C becomes C sub 1. So I guess this one here, I'll relabel it as D. And there it is. You might be wondering, well, why are some points blue and some black? And this has to do with free and fixed points. If I grab that point, I actually can't move it. And the reason is because it's dependent upon where A, B, and C, A, B, and D are, right? Um, that's just by construction. Of course, B is not dependent, D is not dependent, and A is not a dependent point. So that's the reason, remember that C is dependent upon where A, B, and D are. So hope that makes sense. But once you have it drawn in, of course, you can do all kinds of fun things. Like I can right click and drag, copy the whole thing and color it something different. Oh, let's make it red. That'd be nice. I can also, change segments lengths, or I guess styles. Let's make it a little thicker so it shows up a little heavier. Of course, if you were using this in a class, you might want to, make these labels a little bit bigger. So I change the font size maybe to like 28 is what I usually do in class if I'm projecting this on a board. So some things that you could do here to change your picture. Well, the last thing we want to do is we wanted to investigate the diagonals. So I'm going to add a segment as a diagonal. I'll say that's a diagonal, another diagonal. And it appears to me like these diagonals meet at a right angle. But to check that, I guess what I would do is I would measure that angle and see what happens. So I'm measuring the angle here, and sure enough, it is a 90-degree angle. And so there it is. Seems like diagonals meet at a 90-degree angle. This might be something that you actually teach if you're a high school geometry teacher. The other thing that seems to be true is that the diagonals seem to be bisecting one another. And to do that, what I'd probably do is I'd probably measure the distances between the diagonals and where the diagonals intersect. I'm going to first name this point E. So point E, I'll show label. There it is. And then what I'm going to do is I'm just going to measure the distance or length between A and E, and it just pops in there, 5.64, and between E and C, and that's 5.64. B and E, that's 2.68, and E and D is 2.68 as well. So we get something that looks like this. But the big question is what happens when I drag, and of course you see that this is all dynamic. Since ABCD is defined to be a rhombus, if this is a property of rhombuses, then those lengths better maintain. They must remain consistently bisecting in 90 degree, and you can see that that seems to be something that is true. So it seems to me like we've got a pretty good idea about about the properties of the diagonals of a rhombus. So what we were supposed to do next was to include a checkbox. So the checkbox is going to be this thing that's going to show and hide the diagonals. So that's what I'm going to do. I'm going to put a checkbox. If you hover over any one of these, it'll tell you how to use it. It says select a position. So I guess I'll select a position here. And then it says caption. So I'll say diagonals. And then what do we want? It says select objects in construction or choose from a list. This is the list of all the objects in the construction. You can choose those. But usually what I do is sort of just drag this off to the side, and I click on the things I want to include. So segment J and segment K are the two diagonals. And then I guess what I'm going to do is include point E in there where the diagonals meet, and I'll hit apply. And so I get this checkbox that when I use my move tool, it's going to show and hide those diagonals, which is kind of cool. So I'll leave them hidden, and then what I'm going to do is put another checkbox in and say diagonal properties. And here what I'm going to do is show and hide all of these things that we discovered, which are this length, this length, this length, that length, and this angle. I want to make sure I got the angle. Yep. And I'll go ahead and hit apply, and let's see if it's working. Yeah, there it is. The diagonal properties are there. Here's the diagonals. So that means that I could sort of use this to sort of teach or at least investigate. And that would be the diagonals. So now I can investigate the diagonals, see if I can figure out what we think are the diagonal properties, and of course there's the properties that come in last. All right, so it's a crash course in the use of GeoGebra, but this is the idea that using GeoGebra you can create these incredible dynamic objects that point towards I guess theorems to be proved, or properties that you might be teaching in your courses. In this particular case, it seems to give a good evidence that the diagonals of a rhombus bisect one another in a perpendicular sense. So that's about all I have for today. Please email me if you have questions, and I'll put myself back on screen. And I look forward to seeing what we do this week, and please reach out if you have any questions. And I'm really excited about the course and look forward to working with each of you. All right, have a great week, everyone, and we'll talk to you next week.